Thank you. Thanks for the kind intro. So can people hear me okay? Yeah, in the back? It sounds loud. I'm a little sick, so that's why I avoided shaking hands with people. Thank you for the kind intro. It's certainly a great pleasure to be here. One of my earliest memories of being in graduate school, which was now in a different century, was before there was the web and papers were easy to find. You would spend a lot of your time in graduate school trying to find conference proceedings, printed conference proceedings. These were very valuable to have. And I spent many a day looking for the USENIX, then winter and summer conference proceedings, because they were just full of so many interesting papers, and it was very hard to find those. So it was very fond memories thinking back to those days, and very exciting to be here today. So for those of you who don't know me, I'm Remzi Arpaci-Dusseau. I'm a professor at the University of Wisconsin, where I've been there for about 20 years. I'm also the chair of the department. Apparently, as you get older, you end up chairing more and more things. I'm now the chair of the CS department there. I've been doing that for about 1 week, so I don't yet know how that's going to go. And actually, we're also, beyond our department, we're actually forming a new school of computer data information sciences. So a pretty exciting time at University of Wisconsin. And today, what I'm going to talk about are some research that we've done, but I'm also mixing it in with some advice that I tend to give, like to, say, people who are students, who are newer to the research process. So I'm going to try to mix some thoughts on how to do research with some of the research that we've done, and we'll see how that goes. Your mileage may vary on the value you get out of such advice, but I know it's certainly been useful to us to think about these things over the years. This is all joint work out of our lab, the Arpaci-Dusseau systems lab, I guess. That's led by myself and my wife. So ever since we've been at Wisconsin, we've worked together on everything. And you know, at first that actually caused problems at the university, because they're not used to, like when we were going through the tenure process, every year we would get feedback saying, you know, it's great that you're doing all this work and whatever, but we don't know who's doing what. We basically just ignored that advice. Of like maybe separating our research tracks, because we liked working together, and we figured what's the worst thing that could happen? We could, you know, get kicked out of the university and have to move to California or Seattle or something like that. So we kind of ignored that advice, and then at the end, finally the university relented. In fact, when we got promoted, the letter from the dean said, it's my unusual, in fact, unique privilege to promote 2 people with 1 letter. And I don't know what to make of the fact that he sent it just to Andrea. So it's a true story. I never got the letter. So before we kind of get into that advice and a little bit about our work, I'm just going to say there's 3 things to know that I'll start with. The first is something that we all kind of know. Research is hard. It's hard to do research because coming up with an idea is hard. And when I think about ideas, what I think about are, you know, novelty, basically 2 things. Novelty, how good is the idea? And then quality, how good is the idea? And if you think about these axes, you know, coming up with something that's new and not such a good idea is actually, that's pretty easy. That's probably the easiest thing to do. For example, let's say we invented a social network that connected billions of people together and then caused the downfall of democracy. Oh, that's actually not a new idea. So maybe it's harder. Maybe it's hard to come up with a new bad idea. What's a little bit more interesting is when you come up with a good idea that's not new. And I think a lot of people who've been in research, even for a little while, this happens. You have this great idea. Hey, when we're writing out data to a hard drive, we should do it in big sequential chunks, because that way, and organize that in a log. And that way we'll avoid seeks and we'll get really good performance. And of course, you run and you tell your advisor, and your advisor said, that is a great idea. It was published in 1993. Hello? That happens. In fact, what happens as you get into the research process is you can tell you're making progress, because how long ago the paper that you kind of ended up creating in your own mind gets nearer and nearer to current time. And eventually, you cross into the future, and then you have a new idea that's a good idea. And so, quote from Einstein, if we knew what it was we were doing, it would not be called research. So research is hard. I think research is also hard work, and that's something we also all know. Here's a quote from Ira Glass, the creator of This American Life, a great radio program. And he says, it's hard to make something that's interesting. Basically, anything that anyone makes, it's like a law of nature that anything that's written or anything that's created wants to be mediocre. It's all tending toward mediocrity. the way that all the atoms are dissipating out toward the expanse of the universe. Everything wants to be mediocre, so what it takes to make anything that is more than mediocre is an extreme act of will. You just have to exert so much will into something for it to be good. So research is hard, and it takes a lot of work, so we should just accept that. And the third thing I'm going to talk about just before we get into the details is a little bit about the research process. Now, when you think about the ideal process, it might go something like this. You find a problem to work on. Because we're a systems community, we build a system to kind of address that problem. We evaluate it to show its benefits. We write up a paper, submit it, it gets accepted, and profit, of course, at the end. And of course, what actually happens is a little bit different. All the same steps, basically, but there's a lot more kind of back and forth than you might think at first. So when you're finding a problem, you might think about a problem for a while and then realize, actually, that's not a good problem, and move on to the next problem. Or you might find a problem, build a system, start working on the system, and then realize you're not actually solving a real problem there. Or you might get to evaluation and then realize the thing you thought you were doing isn't going to work, and you go back to step one again. Or you even might be at a stage where you're writing up your ideas, and there's something about writing where you try to really list what it is that you're doing and how it's different from the past that sometimes makes you realize, oh, we really didn't advance the state of the art, and that certainly happened to us. And there's many other places where this kind of feeds back and forth. You might be evaluating and then realize a better way to build a system. You might be writing and do the same. And in no case is profit a part of it. So if you're going into the business for profit, that's the wrong thing. So the focus of this talk, it's a little bit hard to see the red. Is that true? Sorry about that. That's not going to change, and it's going to remain hard to see. Hopefully I won't have too much red, and I'm sorry I didn't check that ahead of time. So what that says is the focus of the talk, and it points really to points 1, 3, and 4. So I'm going to talk a little bit about the kind of advice and so forth about finding problems, because that's a very hard thing to do, and I think especially for newer people, it's one of the most challenging things. I'm going to talk a bit about evaluation, and that's where the title comes from the talk. I said measure, then build. And a lot of times that's because in our work, we found that measurement not only can be good at evaluating the existing system that we're building, but has really driven the creation of new problems and new ideas in a way that I think can be really beneficial. I'll talk a little bit about point 4, which is kind of a communication, learning how to write and talk about your work. And interestingly, I won't talk too much about the building the systems part, because I think a lot of people who get into systems, that's the part that they know best, and that's the part that they do best naturally. And so therefore, I won't spend as much time on that. Okay, so now we're into the rest of the talk. And I just threw a slide. I threw my mouse, sorry. Let me go back one. And then I'm going to just give a few pieces of advice, and then talk about each, and maybe give a few examples, and then hopefully finish up in time. And then if we have questions at the end, sure, take those. So the first one is going to be find inspirations. I think it's really useful when especially when you're young and new to something, is to find examples of things that really push you forward, that you wish that, oh, if I could only do a paper like that, or give a talk like that, or write a paper that's as clear as that one, that I would be happy with myself. And so finding inspirations is important. So I thought a little bit about papers that inspired me very early in graduate school. The first was a paper called The Impact of Operating System Structure on Memory System Performance. This is by Brad Chen and Brian Bershad, way back at SOSP many years ago. And what I'm showing here, and the idea behind the paper is pretty simple. It was microkernels were a new thing again at that point. And the paper was trying to compare from a structural standpoint, like by having a microkernel and a monolithic kernel, can we compare the two and say something about how the structure of those two different types of kernel architectures affects performance? And we can quibble about the details of this paper, but what I got out of this paper and what really impressed me about it was how they did the work. And so the paper started with this table, and you can't quite read it, so I'll zoom in a little bit. It basically is a list of the workloads, a description of each workload, and they're pretty simple workloads of the time, right? SED. We probably wouldn't be excited about SED as a workload today, but back then it was pretty exciting. And what the paper did is just compare the performance on Mach, the microkernel that they were studying, and Ultrix, which was one of the many Unix flavors that was around at that time, long before Linux became the de facto standard. And this table is kind of the beginning of any performance evaluation. You run it on both systems, you see how long it takes. But what impressed me about this paper was that that's not where they started, or it's not where they ended, that's where they began. And what they had to do is go look into it more deeply. And what they found was that in some cases, the reason one system did better than the other was because there was a policy difference, not a structural difference. So they switched the policies to be matching across both systems. And then they looked into it more deeply. They did iCache traces and Dcache traces, and they understood that in the existing mock system, it was the long pathways to do communication that were causing iCache problems that were leading to fundamentally worse performance, at least in these systems. So what I learned from that was how much care is really required to do meaningful measurement. And that always stuck with me, and I'm certainly still influenced by that. Another inspiration, here's a graph from, it's actually from a dissertation that we were kind of reading at that time when we were new to graduate school by Rafael Saavedra Barrera. It's called CPU Performance Evaluation and Execution Time Prediction Using Narrow Spectrum Benchmarking. And what this graph shows, I mean, the dissertation is actually about a lot of things, about how do you predict performance on different computer architectures of various programs. But what they realized in doing that work was one key thing was that you needed to do was to analyze the memory system of the architecture you're trying to predict the performance of a program on. And so what they came up with was this very simple benchmark. It's a 3-line benchmark, basically, for a bunch of different array sizes, for a bunch of different strides through the array, access memory at those strides, time how long it takes average per access, and then plot it like this, with stride increasing along the x-axis and time along the y-axis. And what this did in the architectures of the time was reveal a huge amount of detail about the memory system hierarchy. So how big the caches were, how many levels of caches, how big the line and block sizes were, how big the page sizes were, how much it cost to do a TLB miss, how associative the caches were. All this detail from basically a 3-line benchmark. So what I took from that is that even simple measurements can reveal fascinating intricacies of systems if you can just figure out what to measure. So find inspirations. Now, as you can see, and you may get worried at this point, this is point 11. I'm going to go down to 1, and then the talk's going to be over. We're going to spend more time at the beginning. So if you're getting a little bit nervous that I'm taking way too long and this looks like a 3-hour talk, don't worry too much. Trust me. The one thing I do a lot is give talks and try to finish on time. That's the benefit of being in a classroom environment, right? That you know at the end of the class, the students are going to leave, so you just learn to stop on time. So second point. Talk to industry. This is maybe obvious in the systems community, but I thought worth talking about. People have real problems in the real world. Of course, if finding problems is one of our basic things, it's good to talk to people who have real problems. Engineers and companies work on those real problems, and sometimes, in many cases, they're not able to solve them in the most general or maybe the most research interesting way because they have deadlines, they have their own pressures that they're dealing with. So if you talk to people and learn about what real problems are, the opportunity for researchers is to take a step back and maybe figure out a more general or figure out some lessons that you wouldn't figure out if you were just working on it for your job. This has happened throughout the history of computer systems. If you go back and look at even the most foundational papers by somebody like, say, Dijkstra on semaphores and concurrency, if you read about the history of that, it's pretty obvious that machines at the time that those papers were written had solved many of those problems. There were machines that shipped, very earliest machines that shipped from places like Burroughs that had test and set instructions, that had some sort of support for concurrency for locks and condition variables. But when Dijkstra came to it and could look at it really from this academic perspective and write these very seminal papers, it could really help kind of all shape how the field of concurrency could go forward in a way that maybe would have been hard for industry to do. So our own example, I'll give one, this is where I'll start talking about some examples from our own work. The example I'm going to pick is file system checking, what I often call the ugly stepchild of file systems. Why do I say that? Because it's one of those things that anytime someone introduces a new file system, for whatever reason, one of their goals is almost always not to have a file system checker. No need for checking ever. That line has been used many times. That usually remains true until some very valuable customer has a corrupt image and says, where's the checker? I need to fix this corrupt image and I don't have a backup of it. And then, of course, at that point, the people building the file system build a checker if they haven't already. We all hopefully know kind of what a checker is. Its basic operation is pretty simple. It takes as input a possibly corrupt file system image, and then outputs a repaired and consistent image, hopefully with a lot of the data in it still. And the story I'll tell here is a conversation I remember very distinctly us having with an engineer at some storage company. And they talked about the story of fsck performance. So the story goes like this. The engineer had a call from a customer. The customer was a valued customer. So they said, hey, we have this image, literally like I just said. It's corrupt, and we need to fix it. Can you help me do that? And the engineer said, sure. Type this, with these flags, whatever. Should solve your problem. Customer said, OK. Typed it, hit return. Said, great, it's running. Hung up. That's unfortunately not the end of the story. 2 days later, the customer called back and said, thanks again for your help. Engineer said, great. And the customer said, I just have one question. When is the checker going to stop running? So that stuck with us. We're like, that's very interesting. Maybe fsck performance is an interesting problem to work on. And just from that conversation, we started working on it. And we started working on something we called the Fast File System Checker, or fsck, which was presented at FAST some years ago. And we really took a two-step process there. First, we just did a study. And oftentimes our work will start that way. This is that measure then build part of the world that I mentioned in the talk title, which was we simply started by taking existing checkers and measuring their performance on a bunch of different file system images and finding what they take too long to do. And it turns out in checkers there are many things that take a long time. For example, checking if each block that's pointed to is only pointed to by one file. You have to look through all the pointers of the file system. And there's many things like that that take a long time. So we tried to think of that from the ground up, of how can you redo the checker so that operations like that can be done quickly instead of basically doing a bunch of random seeks all over the disk. And there's a lot of details to that, like you do things like group indirect blocks so you can scan them quickly. And it resulted in many cases a much faster checker. It was also probably one of the best stories in terms of kind of impact on some kind of industry, in that we gave the talk at the conference, and then happened to be that a world's file system checker expert was in the audience, and I think was so inspired by the idea that went and actually, in a day, kind of built into the FreeBSD checker what had taken us a year to build in our world, and now I think that's part of the existing checker. So, talk to industry. People have lots of things that they're working on. It gives you ideas to find problems. Third point is read broadly. What do I mean by that? Well, everyone reads papers and listens to talks, and that's why conferences are great, and that's why proceedings are great. You have to keep up with what others are doing. It also helps you directly find new ideas. I remember Jim Gray, famous computer scientist, Turing Award winner, sadly passed away too early. He once talked about a 20-paper rule. If you're interested in an area, find the 20 papers to read in that area, read those. If you don't have any ideas, you probably shouldn't be a researcher. I thought that was a little harsh, maybe, but maybe that's a reasonable thing to think about. But what I'm going to talk about instead is that we should read and learn broadly, not just in a narrow area. And there's this great Steve Jobs quote that I uncovered some years back. If you're smart, Jobs said, what you do is make connections. To make connections, you have to have inputs. Thus, try to avoid having the exact same inputs as everyone else. Gain new experience and bring together things no one has thought of before. So basically, Jobs had been asked, like, if you're a smart person, what should you do? And he thought back to his own experience. His own experience, he went to college for a brief time, but he had taken a calligraphy course. And when he kind of went back and was creating the Macintosh, it became one of the, kind of a revolution in desktop publishing because of its typography. And he always thought back to that time where he thought about those types of things. And he thought that that was an input that most people in the computer industry didn't have, which 100% if you were using computers at the time when the Macintosh was introduced, you would agree with. People did not understand typography back then. So read or learn broadly. I'll give another example in the world of file system checking. Yeah, we did some work on file system checking. By the way, a colleague one time, as they saw another file system checking paper come out of our group, they said this to me. I think they meant it as a compliment. They said, when I hear about what you're working on, it always sounds really boring, but then I read the paper and it was actually pretty good. I never knew quite what to make of that. So in any case, we did another paper on file system checking, and that started when we started looking at file system checkers. We noticed the code was pretty complex and messy, thousands of lines of C code, often low-level code that to some degree no one wants to touch, because if you mess up the checker, that's a last resort tool in many cases for people. You don't want to make it worse. So our idea was to write a checker in a higher level language, and we spent many months languishing on this problem, trying to invent our own domain-specific language to build a checker, and just repeatedly failed. This grad student was unhappy with it. We were unhappy. So this funny thing happened. Our luck was that we have a very strong database group, historically strong database group at Wisconsin, one of the pioneering groups in the area. And they have a pretty regular database seminar, and sometimes we would go to it. And honestly, I would kind of make fun of it, because I would tell my database colleagues, no matter what the talk title is, no matter what the problem was, the way you solve the problem is you put some data in your SQL database and then you ran some queries. And that was what you did. And that's what the database community does. And they always were mad at me when I said that. And then humorously, after yet another talk that felt like that, we were like, what if we took the metadata of a file system and put it in a database and ran some queries against it. And so that's how we came up with this idea called Squeak, a SQL-based file system checker. And unlike our languishing approach, which took months and months and months and got us nowhere of defining our own language, within the first week, we had like the rudimentary foundations of a working checker. It was much easier to write. So we wrote hundreds of SQL queries instead of thousands of lines of C code, much simpler to understand and modify than a typical checker is. And I just thought I'd show a few examples of that. Here's an example of a check that looks for, in a Linux file system, there's a block bitmap pointers, as early Linux file systems. How do you make sure they're in the right range? How do you make sure indirect blocks are, find indirect blocks that aren't pointing to the right thing? Or even more complex checks, like if there's a parent and child directory, make sure if the parent refers to the child, that the child's dot entry refers back to the parent and alert if otherwise. So by reading or listening or to talks or coming at things from different places, you can kind of get new ideas in a way that you might not if you just read narrowly in your area. Okay, so this will probably be the longest point I make in this talk, which relates to the title. And the point here is to use careful measurement. Measurement can drive, of course, the analysis of the system that you're interested in right now, that you're building. But I think it also can be an engine for new ideas and new thoughts and new things you're learning. And so let me give a few examples that relate to that. So I often think of this kind of loop that we do in systems research, which is you build something, and then you measure it, and then therefore you gain some understanding, then you realize what you should have built, and it kind of continues until you're done. And of course, you may start at any point in this. You might just decide to build something and then measure it, or you might measure something first and then understand something about the state of the art in order to figure out what to build beyond that. And I always think of this, the first thing, of course, we have to do with good measurement is explain the system that we're understanding clearly. A good experiment is worth 1,000 words, some famous person said. Osterhout actually had a nice article about this in CACM a while ago, where he said, go one level deeper. This is certainly something we've been doing for many years. I'm going to give a concrete example of that on some work we did on something called membrane operating system support for restartable file systems. So the idea here was very simple. There had been some work on device drivers, which showed that you can kind of build fault domains around device drivers, and therefore they can crash and restart. And Mike Swift had done that work as a graduate student. Now he's been a faculty member at Wisconsin for many years. And we started working together. We said, why don't we do the same thing for a file system? So the idea is that we have an application down there running on an OS with a file system somewhere in there. And the file system, we're going to figure out how to make it so that the file system can crash because it's buggy. And we'll figure out how to restart it. And then the application won't notice at all. So how do we evaluate that? And what we did is we just ran a very simple workload. We're doing random reads to large files. And then we're going to inject the file system crash and restart in the middle of this time sequence and see what the performance impact was. So this looks something like this. Along the x-axis, we have time. Along the y-axis, we have the average read latency. This is on a hard drive in the era of the work. And then you can see the fault gets injected, and then performance gets worse for a while and then becomes better again. But to really explain this, you have to go a little bit deeper than that. You can't just stop at that point, because it doesn't exactly explain what was going on. And if you think about it, and you have a good model of how a file system works, and you knew a little bit about how our restart process worked in this membrane work, you would know that a lot of the system state gets reset at that point. So what we did is we put a bunch of counters on things to look at what was going on. And the interesting factor here was if on the right y-axis here, what we measured was how many indirect blocks were read from disk over the lifetime of the experiment. And what you can see happens after a crash happens, and so we insert this fault and we restart it, we're essentially clearing the file system cache, which includes all the metadata of the file system, like indirect blocks. And so that meant for every random read to a large file, not only were we reading the data block, but we were also reading an indirect block that points to that data block. Those eventually get cached and performance gets restored. And then we've much better explained what was going on in this experiment than just showing the performance. So go one level deeper. Using careful measurement, though, I think is also very useful, not just for explaining the system at hand, but also can lead to new ideas. So I thought we have many examples of that, where we've been doing measurement and paying attention to some little detail of it led us to a new idea. And so let me give this example. This is some work that we did called Improving Storage System Availability with D-GRAID. And this was a pretty simple idea. It was in a RAID, instead of blindly placing blocks, oblivious to whether they're part of one file or this directory or whatever, like most dumb storage systems would do. We've been working on something, a line of work called semantically smart disks, where the disk system would learn more about it would figure out, oh, these are blocks of the same file, or these blocks are of this directory. So it would know some semantically meaningful things about the data placed within the volume. So normally you would say stripe a file across the disks of the RAID, but what D-GRAID did was place semantically meaningful things like a file within, say, a boundary, a failure boundary, like a single disk. So that meant if another disk failed, it would take out some of the file system, but it wouldn't ruin the whole file system. And then we did things like, instead of just having a single directory copy, we would widely replicate the directory so you could always traverse the whole tree. That's what D-GRAID did. But I'm not going to talk about D-GRAID. This is how we're using measurement to find a new idea. And what we were doing was we were measuring file system reaction to D-GRAID faults. So down here we have a D-GRAID volume, and it has 3 different, we'll just make this a really simple file system. It has a super block, it has inodes, and it has data blocks. And it was this observation that led to a long line of follow-on research, which was very simply this. When a read was issued to, say, the inodes portion of this Linux file system that we were using at that time, if it failed, and then we, say, repaired the volume underneath the file system, even if we somehow got the file system to want to reissue that read, it wouldn't. It just never would retry. So that's what that red says there. It says no retry, no matter what happened. And that's somehow whoever was writing the code for that part of that Linux file system had a sense that if the inode block went bad, I'm never going to trust it again. Differently, if a read was issued to a data block, let's say just a user file, what the red wording says there is retry. And what would happen is that if you issued a read and it failed, but then you repaired the volume underneath that, the file system would be willing to retry it again later if you issued another read. That was a different policy. Retry for data blocks, no retry for inodes. And like a lot of things, if you pay attention to the details, it kind of generated a lot of questions. We had never heard of a file system failure policy like that, even though we've been teaching about file systems for many years. And so we started to ask, how can we learn more about that little observation in the D-GRAID work? And so we developed a methodology called type-aware fault injection, where you just, for all the structures of an on-disk file system, you inject faults in them, you measure the behavior to that, and you see what happens. And then you can look at different file systems and see what different kinds of policies they have. And so that led to some work on something we call iron file systems, which was published not that long after. And I think that was one of the first papers to show how file systems really react to different kinds of localized disk faults. We uncovered different policies, we found bugs, we found design flaws. And these kind of crazy tables show different file systems and how they would react. So there's a key in the bottom left that shows different reactions to failures. Like, for example, the horizontal line means that the file system halts when there's an error. Vertical line means it returns an error to the user. Diagonal line means you do a retry. And you could kind of notice some things that are similar or different across different file systems. For example, the ext3 file system we looked at, whenever a certain kind of failure happened on a read, what it would do mostly is remount the file system read-only, so it's a halting behavior, and then return an error to the user. This riser-fs, which we were measuring back then, would just panic every time something bad would happen. It would just say, that's a bad problem, I'm going to panic. And you could see almost all the file systems we had some zeros in them, which meant there were cases where they just didn't actually pay attention to the error at all. So lots of bugs. So measurement can lead to new ideas, and there's a long line of research that followed where we do that kind of analysis of systems that leads to understandings of their failure policies. What measurement can also lead, and this is the third point I'll make about measurement, is to learning opportunities. A lot of times you'll get into something, you'll start measuring it, and then you'll understand something deeply about it that you hadn't understood before, and that learning opportunity, in turn, will turn into a new idea. So what I always say is, remember that research is a learning exercise. When you're a student, you kind of view research and education maybe as a little bit separate. But really what research is learning a lot about something, and then eventually teaching yourself and then the community something new. It's actually a very similar process. It starts with deep knowledge of something. So in that iron file systems work, where the learning opportunity came, it came out of some performance study we did. We were building what we called an iron file system, which was just trying to do something very simple. Even on a single, say, hard drive, which was the technology of the time, you could do the same thing on a flash today. We were doing things like adding a parity block for every file, so that even if like one block was corrupted, we could recover from that, detect and recover. That led to a problem, which was the performance of the file system was too slow. And what it really led to was our understanding that we need to know more about how, at the time, Linux file system journaling worked. And so we just started studying that. That was our learning exercise. And so we probably all know what journaling file systems do, but I'll just kind of go over it really briefly. They provide crash consistency, which is, the way I think about that is we're doing a series of updates to a file system state, and we want to make sure that, say, all the updates happen or none of them. We don't want these in-between states, which leaves the file system in an inconsistent way, an inconsistent state. So the way we do that is we use a write-ahead log, or a journal, as it's called, to record some kind of information about the pending update. And if a crash occurs, maybe replay, if we are using a redo style logging, what's in the log to do a repair. And there's many other styles of this, but we're not going to get into the details of that. The example that we then thought about to learn more about it was just a simple workload, like appending a single block to an existing file. And you can think of that in a typical file system as doing a few different updates that have to all happen or none of them happen. So updating a bitmap, say, to mark a block is allocated, updating an inode, say, to point to a new block, and updating, of course, the data block itself to add the new data to the existing file. How that works, as I'll show in this diagram, is on the bottom we have the disk-based file system, which I think of on the left as having a log or a journal, and on the right having the file system proper. And then what happens is data and metadata get kind of put into memory above, and we have to reflect them down to disk in a particular order in order to safely be able to recover. And in Linux ext3 and 4 ordered journaling mode, the order is like this. First you write the data, then you write what we'll call a transaction begin block and the contents of the metadata that's getting journaled. We're not journaling the metadata here for various performance reasons, which I won't get into. When that's on the disk safely, then you issue the commit block. When that commit has reached the end block has reached the log, what you can do then is safely checkpoint or overwrite in place the metadata. And what you know, of course, all those steps, I'll go through them again and explain them. All the steps are kind of required for reasons. You write the data first because you don't want to write the inode that points to that data before the data, because if you do, you could end up with garbage in the file. You write the transaction begin and the contents of the journal first, because you don't want to issue the transaction end block with that initial write, because if you do, you might end up with just the very unlucky case where the begin block and the end block were recorded on the disk, the drive loses power, the contents are garbage, but it looks like a valid transaction. So you wait for that first part to go, then you commit it with a separate write, then you overwrite in place last when you're done and you know you can commit. And if you crash, you'll either have enough state in the journal to recover, or you'll have lost the data and therefore you won't have any of the update really, except the data block. So when we were doing this work and carefully studying its performance, we realized that write ordering, all those steps where you have to wait for something, led to certain kinds of slowness. And the idea that the student had who was working on it was, well, why don't we use checksums to replace some of that ordering? So compute a checksum over the journal, and then write the journal metadata and the commit block together. And if upon crash, what you do is you redo from that entry only if and only if the checksum matches the contents. So how does that look? Same stuff in memory. We write the data, but then we write everything to the journal at once with the checksum in it, and then we do the checkpoint. So we've saved one step, and we've improved performance in that case. And this was kind of this fun thing when the student did the work. Soon after, the people were working on Linux ext4 said, hey, can we borrow your code? And they kind of sucked it into Linux ext4. So use careful measurement to understand what you're doing, for sure, but also to kind of create new ideas and to find opportunities to learn more about what you need to learn to even create even further ideas. I'm going to talk a little bit about finding the best problem. I think it's pretty easy to work on something that's not quite the right problem. One of the first pieces of advice I got in grad school was, there's our field is filled with smart people, so probably the best way to differentiate is make sure you're finding the best problem to work on. That was from my advisor, it was Dave Patterson. And instead, when you're working, think about what's the newest thing and the most interesting piece that's in there. So I'm going to try to give one example. This is very recent work. Where we're looking at this question. We just had this question of, can operating system locking cause denial of service? And we're going to start by doing measurements, as we often do. And the idea is there might be a lock inside of a shared infrastructure, like an operating system. Process one might, through normal system calls or whatever its normal behavior is, acquire that lock. And if it's somehow able to give the right arguments or do something in a certain way, it might be able to hold on to that lock for a long time, therefore causing P2 to be blocked. And that's a problem with normal processes on an operating system. That's maybe even a further problem if you're using kind of containers that are very much from different entities running on the same OS infrastructure. So we were interested in that. And we actually found through measurement a particularly troublesome lock, the Linux file system rename lock. It's acquired during these kind of complex cross-directory renames, which is global at a VFS level. And the problem is that that lock can be held for hundreds of seconds. We have very simple cases where you can cause that lock to be held for a very, very long time. And our initial thought was, well, why don't we just kind of rewrite this and use finer grained locks? And I think there are two problems with that. One, clearly people who built the system already knew about that and could have, if it were easy to do, they would have done it, right? And it turns out to be hard to do. It's also like kind of not that interesting of a solution. So if you kind of force yourself to find like what's the best kind of solution to what you're doing, you might think of something that's more general and more interesting. So what we came across was maybe what we think is a more general lock fairness problem. And it's something we started calling lock usage fairness. Just imagine in the more general case, thread 1 holds a lock for 100 time units, thread 2 holds a lock for 1 time unit. And you repeat that behavior, these two threads competing for the same lock. If the one stays in the critical section for 100 times longer than the other one, it's going to dominate the CPU usage, which may not be what your scheduler policy goal was or whatever. So even if the locks are acquired fairly, and there are many locks that give you fair acquisition properties, like a ticket lock, for example, you're not really sharing the CPU in the way that you expected. So we started looking at how to build locks that are used fairly. We call them fair usage locks. And the basic idea is that there should be a notion of a lock opportunity window. So there's a time when you can acquire a lock, and if you hold on for a lock for too long, you get penalized. You can't just reacquire it immediately. So then what that might look like then is if each thread has its lock opportunity window, even though they have different lengths of time they spend in the critical section, they end up still kind of sharing the CPU in a certain way. Now, this paper keeps getting rejected. So maybe this is terrible advice, but I think it's kind of an idea where we came to it was my best example of something that we felt like we came to a better problem by thinking about it a little bit more than we would have just initially by solving it. So try to find the best problem to work on that's going to push your research in the most extreme way. Okay, so the last so many pieces of advice are all a bit shorter, I would say. And maybe, maybe in some cases more general than just research advice. So find mentors. This certainly starts in graduate school. The advisor-student relationship is one of those central things. And what do the people who give you advice do? They should give you advice. They should help you how to find problems. They should help you learn how to communicate. They should give you lots and lots of critique, right? Critique is there to make you better. And of course, one thing I like to point out to students particularly is every person who gives you advice has strengths and weaknesses. So you have to learn what those are and learn what advice to pay attention to and what advice to listen to but not necessarily follow. As Tolkien, I guess this is the theme of the morning, is that we have references to The Hobbit, etc. Advice is a dangerous gift even from the wise. So I thought I'd just try to think of a couple examples of that that I benefited from in my career of listening to advice or ignoring advice. So some cases where I listened to advice, I asked my advisor on the first day of grad school what's the best advice he could give me about how to succeed in grad school, and he said, well, sink or swim. There's a lot of smart people here. You have to work really hard to keep up. It was kind of a bracing way to begin grad school, but I think probably a good lesson to hear. Another piece of advice I heard lucky to hear from all these wise people was Jim Gray on dissertation writing. Writing that dissertation is a very hard process, really, at the end of your graduate school. And so the advice he gave, which I try to give to every grad student that I know, is to first work inside out. So write the content first, and then the intro, conclusions, and related work after. Of course, he also said that he reads it the opposite way. Like Jim Gray used to read, when he read a dissertation, he would read the intro to see if there was an interesting problem. If it was, he would read the conclusion to see if the person learned anything of value. If he then found that to be of value, he'd read the related work to understand what the context of the work was, and then only then would he go into the middle part. And then the other thing he said, which I think is really useful too, he said find a good example of a dissertation and a bad example. So the good example is the one, like what I said earlier, finding inspirations. Like find something that when you're like, I wish my dissertation could be as good as this one, so that the day you need that uplift, you can look at it and say, I'm going to get there. And then find a bad example, which you can say, when you look at it, you could say, well, I know at least mine won't be as bad as this one. And yes, it's true. There are some dissertations that get through the process that aren't that great, and it's nice to know about those because there are absolutely days you're going to hate your dissertation. A case where I ignored advice was one I'll share with you too, which is at one point after about 5 years in graduate school, Patterson, maybe he got a little bit sick of me. That happens when people hang around with me a long time. And he said, it's time to graduate. And I was like, no, it's not. I didn't know that that was a little bit weird to say as a grad student, but I really wanted to do one more piece of work. I had kind of come to grad school as more of a computer architecture student and had been moving more and more towards systems research. And I really felt like I wanted to do one more thing that was really firmly in that world. That led to my dissertation on this system called River, which was kind of this pre-MapReduce data processing system. And more generally, it really led to a lifelong interest in storage and I/O. So by ignoring that advice, not just saying yes, thank you. And of course, Patterson being gracious enough to fund me for another year, I benefited by not quite listening to that advice. So find mentors, get advice from them. This is useful throughout your career. Don't have to always listen to the advice, but you should think about the advice and then decide what to do. Embrace rejection. We are in a rejection business. Now, all of you successful published authors at USENIX ATC don't know this, but sometimes papers get rejected at these conferences. A typical conference has some hundreds of submissions and say 40 or what are we up to, 70 in here, which still isn't that many if you think about it. That's still a lot of sad people at the end. So rejection is the common case, and it demands thick skin. Learn from your mistakes, avoid perfectionist thinking. That critique is there to make you better. Great Samuel Beckett quote, ever try, ever fail, no matter, try again, fail better. A friend of mine, Brian Noble at the University of Michigan, had these great laws of handling rejection, so I'll share them with you here. Basically, take each piece of advice and you should be able to say one of these three things. One, this is a great idea. This is how we're going to incorporate it in our paper from a review. Two, this is a great idea from a review, but it's so good we're going to put it in the next paper because it doesn't quite make this paper better. And three, our paper led the reviewer astray. Here's how we will fix the paper for the next time. You notice in no case is there option 4, which is the reviewer is an idiot. That is a terrible way to take a review. And I always find this really funny. What I always say to somebody who says, hey, this reviewer is an idiot, I'm like, why do you keep submitting your papers to conferences who are full of idiots? Why do you want to be in that group so badly if they're all idiots? Clearly, they must not be that idiotic if you want to be a part of that group. So it's a bad way to look at it. A good way to look at it is we just wrote it in a way that they didn't get it. And that's a much healthier way to look at it. Of course, once in a while, you want to vent, but most of the time you shouldn't. And there's a quote from a movie that I like. It's called Jacob's Ladder. Probably most of you haven't seen it. But it's, I think, apropos. It's if you're frightened of dying and you're holding on, you'll see devils tearing your life away. But if you've made your peace, then the devils are really angels freeing you from the earth. It's just a matter of how you look at it, that's all. So reviewers are actually angels, not the devils that you sometimes think they are. In any case, there's a really nice example of this. I was looking for one that talked about the review process and how it can be really positive. And really the best example I found was from Dave Anderson at CMU. It's about their FAWN paper, a great paper that was published in SOSP 09. And what he shared on his blog post was actually the review process of OSDI 08, the year before. And this is what I'll show is review quotes that he gave and then his response to the review. The review said, as it stands, it will need serious amounts of both rewriting and, more importantly, real technical work to make it into the truly great paper it should and perhaps could be. Anderson's response, which I think is super interesting, is if you have the chance to honestly say something like that in a paper review, instead of just being harsh, do so. Anyone submitting a paper is inviting criticism, not just of the paper, but of the work. And when your paper is rejected, you always end up asking, is this work worth continuing? It's very helpful as a reviewer to be clear what you're talking about, when you're talking about the paper as submitted being bad or the idea in general being bad. Don't assume the authors are as robust as you. They may be first or second year PhD students submitting their first paper. You probably freaked out a bit the first time you had a paper rejected. I know I did. And then the second thing he said from the review was, he took this quote from the review. The PC liked much of this paper but felt it was premature. Please focus on finishing the work itself. Bringing out what's interesting and novel from the perspective of software architecture and scaling to a larger number of nodes. The PC looks forward to seeing the improved, mature version of the work at the next major conference. And Anderson's response, which I think is so mature, and I've always pointed this to students saying this is like how we should be, is this was one review when we read it and sprinted back to the lab to try to make the best damn paper we could write. So what a great response. And in fact, where I first noticed this was I noticed in the SOSP 09 paper on FAWN, they actually thank the OSDI 08 program committee. Very unusual to basically point out where your paper got rejected as it got there. And then I really appreciate that he wrote this out. So embrace rejection. Rejection is part of what we do. It's okay, like we said at the beginning, it's hard to have good ideas. So they're gonna be rejected sometimes, it's okay. Improve your communication. This is pretty obvious too, written and oral. Of course, well-written papers are more likely to be accepted. And this other thing is that people sometimes don't appreciate is when you write down thoughts, it just really helps clarify what you're trying to do. There's a great quote, "I write to discover what I know." And that's happened to us many, many times throughout our career. Of course, that's also in terms of oral communication. Give as many talks as you can. That's why it's great to be a professor. Whether you like it or not, you're in front of a class, you get to practice talking all the time. It's okay to be nervous at first, get feedback on these things. Hamming said famously, you should spend at least as much time in the presentation of the work as you do in the work itself. So you should spend like half your time talking about your work and communicating about your work, otherwise no one will know anything about it. My example of that is my first talks that I gave in my life. As an undergrad, I didn't really give many. I remember one particular one I gave in a German class. This was a class with 8 students in it, and I had to give like a 5-minute presentation in German in front of these 8 students and the professor. And I literally almost passed out just walking to the podium. I was so nervous. I'm like, I'm not going to be able to do this. I only wish that I had a video of this so I could relive the tragedy of that German talk that I gave that one time as an undergrad. And then I arrived at grad school. And of course, why is that? Like, I went to grad school and I'm like, this is fantastic. I'll finally get to just focus on doing technical work, none of this other stuff where you have to talk or write or any of that business. And the first week, my advisor gave me an assignment, which was, hey, we're starting this new project. It was called the NOW project, Network of Workstations, where we're starting to understand that clusters might be useful to build large-scale computer systems. And he's like, why don't you read about network interfaces and then give a talk to the group the next week? Now, not only did that tickle my fear of giving talks in public, but it also was the case that in terms of network interfaces, in the room, there were going to be many experts in network interfaces that knew way more about network interfaces than certainly I did then or even I do now. So it was a tough audience, and my reaction to that, of course, was, oh, I have to quit graduate school. I've been here 1 week, and this worst thing that I imagine happening, and somehow I stumbled through it. And now, like a lot of times I tell this story to people, and they're like, you look pretty comfortable now. It sounds like you're making this up. And it's literally just practice. You just practice, and at some point you realize, I can't even see who you are if you're sleeping or whatever. So you just get over it. It's not that big of a deal. I've made many mistakes in public. I say all sorts of stupid things. I'm still going forward. So improve your communication, and mostly through practice. Last couple points. How am I doing on time? I'm doing okay on time. I'll finish soon. You started late though, didn't you? I started, yeah, okay, all right. I blame Dan. So find what you like and find what you do well, and both of those things are important. So a lot of research at the beginning, you have to develop taste, like figuring out what you actually want to work on. And there's a great quote from Eric Kandel. He's a Nobel Prize winner in biology, and he has this fascinating and to some extent heart-rending autobiography, which you should certainly read if you can. And the quote that I took from that was, maturation as a scientist involves many components, but a key one for me was the development of taste. Much as it is in the enjoyment of art, music, food, or wine, one needs to learn what problems are important. I sensed myself developing taste, distinguishing what was interesting from what was not, and among those things that were interesting, I also learned what was doable. So it's interesting he talks about both those things, about developing taste, figuring out what you want to work on, and then also what you can do. So he wanted to learn about brains. Instead, he studied those sea slugs at the top. He wanted to learn about human brains. They're too complicated. So instead, he studied the full neural circuitry of that sea slug, and that's why he won a Nobel Prize. And so finding what you do well is kind of related to that. It's related to things you're interested in, but you have to be able to do it well, right? And that requires some level of self-awareness. Those who do good science do so because they choose problems that are suited to them, said Lee Smolin in his fascinating book called The Trouble with Physics. So our example of this was a student. A student was working on something, a project we were calling the student's name is Tanu, and he was working on this thing called fractured processes. The idea was to carve a monolithic process down into smaller components and then have each of them be restartable, much in this kind of micro reboot work that people had done, kind of a follow-on to that. And really, we spent years on this, a couple of years. Student was totally frustrated. Paper kept getting rejected. Eventually, we published in Trios. It was like, finally, we got done with that work. And the poor student was then faced with this, I'm not sure I'm going to get a PhD. And what we kind of came to is, let's just try one more problem. And he started working on crash consistency, and it really kind of took off like a rocket. And we wrote a paper that ended up published at OSDI on this tool called Alice, and then some follow-on work. And it's really influenced a bunch of our subsequent paper. And he was amazing on all this work. And the success really came, it wasn't just the factor of the student, it was the problem matching the student. And I think that's something you always have to think about. What are you interested in, but also what can you do well? And if you don't match those two things, it's often troublesome. Now, that's a little bit problematic advice, because for an advisor, you're always trying to judge, is this student going to kind of get through the PhD process? And if it just turns out they're working on the wrong problem, you have a very fundamental problem. You can't just judge them and say, hey, this isn't going to work out. You might be that they're working on the wrong problem, right? And so that's something that certainly I've thought about a lot. So I was going to talk a little bit about Alice, but I'm going to skip that part for the sake of just getting done kind of on time. But you can read about it. This just kind of shows, if you're just trying to update a file atomically, actually how much work it is, like to write a correct file update protocol at application level. And that's what we studied in that work. It requires a lot of thought other than just overwriting the file. So, and that was Alice's summary. So that work then led to that we understood these things called persistence properties that file systems have and exposed to applications. We studied application update protocols, and they were all very varied and had vulnerabilities and bugs that assumed things about file systems, and that even battle-tested applications like databases that have been out in the field for years had bugs in them because they were assuming something about file systems that had changed. So sorry, I can't talk about that more. So find what you like and find what you do well, and think about both of those things. Okay, last couple points. Next last point is listen. Listen is a little bit more general than just the research process. It kind of relates perhaps more to teaching. I've noticed this, though, and I've gotten a great benefit in my life of interacting with a lot of very well-known researchers, like my advisor, Jim Gray I mentioned a few times. How lucky it is for any person to be involved with such people and get to learn from them. And what I always found very remarkable about them, these are people who can be as articulate as anyone else, make a forceful point as anyone else, talk compellingly about whatever they're working. And what these people I always found did was that they were willing to listen to you when you talk to them, and then hear what you're saying, and then react to that. Jim Gray, for example, when he would come to Wisconsin after we were new professors there, and he would just say, make sure we have some hours for the grad students. And he would sit with grad students for hours and just talk about what they're doing. And how remarkable is that for someone so successful to be so willing just to spend hours in the details with people? So listening is good. And our experience I'll give with that was kind of a teaching story. Teaching and research are really quite related, actually, that when you repeatedly revisit fundamentals of things as a teacher, I think you think about them differently and therefore can make your research better. And it's also an opportunity to listen. Listen to students ask questions about material. Every time a question's asked by a student in a class, it means you didn't quite explain it properly. And so there's, the way I like to think about it is when I used to think about teaching, I used to think it's the professor telling the student something. But really, it's a cycle, right? You say something, the student asks a question, and then you learn better how to say those things so those same questions don't come up. Our experience, which Dan mentioned at the beginning, was with this free operating systems book. It's developed. We didn't really set out to write a book. It just kind of happened organically, and all because students kind of asked questions. And you can buy a hardcover now. We print it ourselves. It's downloaded a lot, whatever. But really how it started was these two questions, one asked by two different students. And I'll just share. This is really my last story, and then I'll say thanks. The first student that asked this question, I'd been teaching the OS class for some years at Wisconsin, and Andre and I had been developing our own kind of lecture notes. But we just used one of the standard textbooks. There's many out there at the time. And one student asked me, is this book required for the class? Is this textbook required? And I said, well, look, I teach stuff in class, and it's not like we're following the book. We have our own notes that we're following, but it's nice to have a different source, so kind of, yeah. But for whatever reason, I kind of tried to listen to the student, and I said, well, why do you ask that question? And the student said, very humbly, I can't really afford the book. And I was so embarrassed of myself that I had never considered that I said, from that moment on, I'm never going to force a student to buy an expensive textbook again. So that was that. I just said, come to class. I'll write on the chalkboard. You take notes. That's how we'll do class from now on. Students seemed kind of excited about it. One less thing to buy. But then student 2 came up about a week later, and student 2 said, well, what do I do if I miss class? I'm like, well, why do you miss class? He said, well, sometimes I oversleep. I said, it's 1 o'clock. This is a true story. I'm like, you can wake up. And he's like, well, sometimes I'm out of town or whatever. Okay, fine. So we had, like I said, Andre and I had developed these notes enough. And so what I just did that semester, because of that question that I listened to, was I would go back to my office and just kind of write down what I had just said. It was right in my head. I could write it down. And I found that I kind of enjoyed that process. And that's why we got to this free operating systems book. So listen. And then finally, it's the people stupid. Of course, all of this work, any work that I talked about, I did very little of it. Like I said, it's with my wife. here's all these PhD students. We've had these amazing, we're so lucky. We've had so many great students over the years, some postdocs, many masters and undergrad students too. They did all the work. And when you look back at the work, it's fun to talk about the technical things you did. But what you really end up remembering are the people. And so at the end of the day, you should remember that, I think, too. So that's my talk. Thank you very much. So I don't know, do we have time for any questions, or do people actually have any questions? Or the next person should get set up, and then I'll be happy to talk to you as well offline. Who's next, by the way? It's lightning talks? Oh, okay, well, whatever, if people have a question. I found that when I give these advice talks, nobody wants to ask questions, but if you have a question, I'd be happy to entertain it.
Well, I'll take a shot. It's Rick Farrow.
Hey, Rick.
Remzi, one of the things that I was struck as I was listening to you when you were going through examples of successful papers is how practical a lot of the things that you came up with were. There were things that could be used in the real world. So you want to speak to, I mean, I don't know whether that was by design or by accident. So you want to speak to that?
Yeah, well, thanks for that question. Yeah, I guess the way we viewed it is, one thing you do when you arrive like at a new institution and you're like a young professor is you have to think a little bit about how am I going to kind of move the world forward? What part of the world am I going to focus on? And I guess what we saw at that time was there was this large systems community that we wanted to be a part of, right? OSDI, SOSP, USENIX, then eventually FAST and the other conferences. So there's a research community we wanted to be a part of. Then we noticed that there was this storage industry which had lots of interesting stuff going on, had lots of actually, resources, people, money, and they weren't that connected. So we did make a little bit of a decision to like, hey, we should go learn about that world, that talk to industry point. And I think that's just always influenced kind of how we do work, is that we say, hey, we start with something that could be connected to the real world instead of just making up a problem. So perhaps that's where that came from. To the extent that we can, we try to do things that are practical because in the end we're systems researchers, right? So that we should be connected to the real world in some way. That probably has its strengths and weaknesses. It may sometimes make work a little closer to the boundaries of what exists today, but it also has that positive quality, I think, of maybe being more realistic. So maybe that's it.
Okay. Hey, yeah. Thanks.
Yeah, thanks.
Hi, Remzi.
Hey, Rez.
I probably don't know, at least my answer to this question, but I'm wondering how you treat it, especially for advice to the audience. But when you measure, how do you know to trust what you measure? And when do you start to think maybe this is too good to be true or too bad or there's something wrong with the measurement and I need to kind of measure the measurement, right?
Yeah.
Who watches the watchers?
Yeah, that's a great question. And of course, you know as much or more about that than I do. So how do you know when to stop? Well, clearly what you do is you do enough until you're like, this paper can get into a conference. Then you're done. No, don't do that. I guess what I've always felt with, and that one example tried to hint at that a little bit, is I remember very early on, one of our first graduate students, back then, this is this funny thing, I used to do actual work. So I would make graphs and build systems things, and that quickly got overrun by having too many students who clearly, when they work on things all day, do it much faster than when I do for 2 hours a day. But so I was still in that mode of, and Andrea too, producing our own graphs. And the student then asked me, how come your graphs look good and my graphs look like garbage? Which was this really interesting question, right? Because I agreed with him. His graphs look like garbage. And what I said was, there's this kind of underlying thing that is true of any good experiment, which is to the extent that you can, you understand what the system is mostly doing. And therefore, when you're doing a measurement, you're really just varying the one thing that you're trying to control for. So that's what good science is. That's what good systems experimentation is. So I was always very careful to get it down to the one factor, and then when you vary that factor, you get the expected curve, more or less. And once in a while, you get something that you don't expect, and that's that learning opportunity, and then you go from there. What students tend to do, I think, at first is they're like, I have to do some measurements. I know that the end part of the paper has that. I've seen some papers that have measurements in them. And so they're like, I measured some stuff, here it is. Instead of looking at it as a process where I need to kind of understand very deeply what I'm doing and then figure out how to measure that. That doesn't quite answer your question of where do you stop. I guess the place we stop is where we feel like we've really explained it to ourselves, and that's a bit it's qualitative, right? So it's hard to automate that. So I don't think I quite answered your question, but that's certainly how I think about it. Okay, so I think we're going to transition. So thank you very much again. I'd be happy to talk to you afterwards.